Following our circuit level discussion of how to build our flip-flops, how to build other types of flip-flops, and what the basic timing parameters of a flip-flop are, let's go over and describe how this fits into a system with our basic timing constraints. Okay, so usually what we have, as I showed at the beginning of the lecture, in a synchronous timing system is we have some sort of a launch register over here, and we have some sort of a capture register over here. Okay, and again, the system will have many of these. So there are going to be many registers that their output goes into a cloud of combinational logic, and there's going to be many outputs of the combinational logic that go into registers, and there are going to be lots of paths. So if this was essentially, you know, a bus of many flip-flops with many C-ins going through, the things are going to be running around reconverging through this logic. They're only going to be going in one direction. There are going to be no combinational loops. Nothing's going to feed back inside the combinational logic, but things will reconverge. So you have different paths going through here, and the paths will come out at many places. And eventually you can always go and mark a certain register, a single bit out of this whole bus, a path that goes through all kinds of gates and comes out and gets to a single bit. So for each path, you can find what the start point and the end point is pretty straightforwardly and easily. And so you can mark you can model our whole circuit as a bunch of these combinational paths, a bunch of these sequential paths from a single start point to a single edge point through a combination of gates. Okay, so that is how we look at the world. We look at the world, we look at all of our sequential system as a big set, a big collection of these circuits that start with a launch point, start with a launching register, go through some combinational logic, and arrive at the end at some sort of an output register, it's sort of a capture register. Okay, so there are two main problems that can arise in synchronous logic. The first one is called max delay. In this case, the data doesn't have enough time to pass from one register to the next before the next clock edge. Okay. The other one is min delay. Min delay is always very confusing at first when you start to hear about it. Stay with me. I'll try to explain it to you throughout the lecture, and towards the end of this section we'll hopefully understand what min delay is about. But it means that the data path is actually so short that it passes through several registers during the same cycle. It's a race. It's a race between the data and the logic, and the clock. The data is so fast that it jumps over the clock and passes into the next stage or the next clock cycle. The important thing here that's marked is that max delay means we have to do something before the next clock edge. It's between two clock edges. Min delay, on the other hand, it refers to the same clock cycle, and we'll see that in a more detailed way and illustrative soon. So max delay violations are a result of a slow data path. These include the setup of the T-setup of the registers, and therefore we usually call it a setup path. So max delay is the real slow stuff. Okay. On the other hand, min delay is a real fast path. Min delay violations are a result of a short data path, causing the data to change before T hold is path. Therefore, it's often called the hold path. So again, max delay equals setup paths. Setup paths. Min delay equals hold paths. Whoops. And this is something that we're going to use quite often. So let's see what makes up our clock cycle when we're discussing a max delay constraint. Okay, so we just have our input here, and again, what I draw the input is just any type of an input that I just decided on. So we have a D that is going to rise at some point. And again, this is our single path from one flip-flop to another flip-flop. By the way, these could be the same flip-flop because the logic could go around and come back into the same one, but there are many, possibly millions of these types of paths in the design, and we have to do this on each and every one of them. So let's see what happens over here. So what happens, we have our clock at some point is going to rise, and we know that a clock rise triggers a TCQ. So the TCQ, we show it as going from clock to Q. Actually, it's the data passing from D over to Q over here, but we know that and the time that what triggers it is the clock pin, so we call it TCQ, as we saw in one of the previous sections. So the clock rose, and point A over here, which is this line, is going to change because D was 1, so it was 0 for a long time, and TCQ later is going to rise. Then there is the logic path, okay? And the logic path has some sort of delay. Sometimes this it's just some sort of a delay that it takes to go through the logic. And you see that it took a while for this data, for this clock edge. It doesn't necessarily have to be a 1, but just for illustrative purposes, to reach B. It went through this delay, this long delay of the logic, okay? And then we have our second clock edge over here. And what we have to make sure that the data is stable, at least T setup before the second clock edge. So we have to make sure that this change at B happened at least T setup before our second clock edge. So what are we looking at actually? We are looking at a race. We're looking at a race between the launch path, that's this guy in green. We call that the launch path. Okay. And we have the data path, well, the capture path, I mean. Okay, this is the capture path. And what we want to know is that the data will arrive early enough at the register at the end. Okay, and this would be called the arrival time. This is the arrival time. And it will be captured by the next clock edge, which this will be called the required time. And what we have to make sure is that the race between the green and the gray lines over here, that the green line is faster than the clock period, which is basically the gray line. Let's put that into a simple equation. We know that the clock period, okay, that's the time between the two edges, has to be bigger than 3 components. Number 1, the delay through our flop, okay, that's the TCQ. Number 2, the delay through our logic, that's the T logic. And number 3, the T setup time, that's the amount of time before the clock edge that we need our data to be stable. And so we see that this is a race between the launch path and the capture path. And we need our launch path to be shorter than our capture path, which is basically the length of one cycle. On the other hand, looking at the hold constraint, as we said before, hold problems occur due to the logic changing before T-hold is passed. It's not a function of a cycle time. It's relative to a single clock edge. So again, we have our same setup over here. And let's see how this happens. And it's going to be a bit confusing or strange at first look, but we'll see how it gets more materialistic down the line. Okay, so the clock rises and TCQ afterwards, the data at point A changes. Then we again propagate through logic. Now this is going to be very short logic, right? This is a short path. Maybe it's just a single inverter. Maybe there isn't even an inverter there. If we have a shift register, for instance, it'll just be a wire there. So this is going to be a real short delay. Okay, but then the point B, the data will change. And what did we have to make sure? That the change at point B happened at over more than T hold after the clock rise. So we take the same clock edge. We do not have any following clock edge here. We say at this clock edge, okay, we want to see that the data did not change anywhere before that, because we're looking now at this flip-flop, okay, and we want to see that B didn't change until T hold passed after this clock edge rose. Okay, this is another type of a race between the launch and the capture path. So we have our launch path, which this time our launch path is going to be really fast. Okay, so this is still a launch path, but it's going to be a fast launch path. It's going to be a fast launch path. And we have our capture path, which our capture path is basically just the delay between when the clock is here and here. And since this is right now ideal, it's going to be 0 or something like that. But we also have our hold constraint. So we need the launch path. We need the clock delay basically to be larger than the hold constraint. Again, this is kind of meaningless right now, but we'll see when we add clock skew, it becomes very meaningful. So again, what we have here is we have this launch path that is basically TCQ of this register, okay? and it's going to be the shortest TCQ possible, the TCQ under like some sort of a fast condition or something like that. The T logic through the shortest path over here, again under fast conditions, maybe a fast process corner with a high voltage and maybe a cold temperature, or if it's temperature inverted, a hot temperature. Okay, and we need that to be bigger than the 0 time that it takes for the clock to propagate between point A and point B, because right now they're ideal, but also including the hold constraint of this guy. So this is T hold of this flip-flop. Now, we saw that T hold is negative, so if T hold is negative and we move that over here, we're going to see we have something positive bigger than 0. That's always going to hold, and so hold constraint is, in an ideal case, is trivial to meet. So as a summary, for setup constraints, the clock period has to be longer than the path delay. We take the clock period T, it has to be bigger than the register delay TCQ, the logic delay T logic under worst case, the longest logic path there is, under slow conditions, under low voltage, under a worst case temperature, which would be high for a high generally, and under temperature inverted it would be a low temperature, and T setup, which is the setup constraint that the data has to be stable before the next clock edge arrives, or the clock edge arrives at the next flip-flop. This actually sets our maximum frequency. Okay, if we have a setup problem, all we have to do is slow down the clock, right? Which means making T larger will help us meet this constraint. For hold constraints, on the other hand, the data path delay has to be longer than the hold time. So we have TCQ plus T logic. This again is the register propagation delay and the logic propagation delay, where this is the smallest logic propagation delay under the fastest conditions, and that has to be larger than T hold. As you see here, there is no clock period in this equation, and therefore if you for some reason have a hold failure, and we'll see why in a minute, you cannot do anything about it. You actually have to throw your chip away. Hold failures are really bad, and that is the largest cause of headaches for chip companies, and it actually you're not able to fix them post-silicon. So as I promised, we're going to understand where hold comes from, where the problem is, and it actually arises from clock non-idealities. So as you can see here, a clock doesn't look so nice as we usually draw it as some sort of a square type of a waveform. It's jittery, jumping around here, right, and so forth. Plus the clock, it's going to two flip-flops, the launch flip-flop and the capture flip-flop, and it's a different signal. There's resistance between the 2 points. It's not something that's ideal that arrives at the 2 points exactly the same, and we can see that here. There is a difference between where this edge passes 50% and where this edge passes 50%. In fact, if we look at it, we'll see that the clock edge, even at the same point, it jitters around, and there are many different points where it, where it rises. So for that, we have a couple of very important type of definitions, and the first one is called clock skew, and clock skew is a spatial variation in temporally equivalent clock edges. It's deterministic and random. Okay, so what clock skew is basically the difference between the time of the clock rise, or the phase of the clock rise on the launch register, and the phase of the clock rise at the capture register, and you see that this skew is non-zero. Okay, so we have a difference in just the spatial arrival of the clock edge at two different registers. They don't arrive at the same time in two different places. And the other thing is clock jitter, and that's temporal variations in consecutive edges of the clock signal, modulation and random noise. It's cycle-to-cycle jitter, which is short-term jitter or long-term jitter. And you see that that's this type of a thing. The same, two consecutive clock edges, their phase will be slightly different for all kinds of reasons. It could be that from one clock cycle to the next, from one edge to the next, they'll move a bit. It could be that over a period of time, your clock cycle floats a little bit and you have long-term jitter. So this actually causes a variation of the pulse width. So we have that big T over there, and it causes it to change, and we'll see how that affects us in a moment. So before I get to that, I just wanted to define positive and negative skew. We usually look at our clock path as we saw before, that this is the launch clock, there's the logic, and there's the capture clock. And we look from left to right, I guess, by the direction of English language writing. And so we look at that direction as positive. Is it necessarily positive? Not necessarily, but that's how we decided to define it. So positive skew is when the clock arrives at the launch register earlier than the capture register. So if the delay is in this direction, we call that positive skew. We take the time of arrival at the capture register minus the time of arrival at the positive register. That brings us a positive number. That's positive skew. Negative skew is exactly the opposite. If the clock arrives at the capture register before the positive register, so if we had our delay in the opposite direction, if we took the time it arrives at R2 minus the time it arrives at R1 and it becomes a negative number, that's negative skew. So positive skew again is defined in the direction of the data propagation from launch to capture. It's just a definition. You could have defined it differently, but this is how we discuss it. So that's so positive skew is when the delay brings to the fact that the capture register gets the clock later than the launch register. So let's revisit our max constraint now that we have this skew and jitter. Okay. So again, we have the TCQ plus T logic plus T setup that are our launch path. But jitter, it's a random thing that can move sometimes, a bit later, a bit earlier, even between two clock cycles. So jitter makes the launch clock later in the worst case. It makes it, because remember, we want to see what our worst case is. So it will lengthen basically our launch path, which means that the data was launched a bit later. So we take the worst case jitter that the edge arrived late, and we want to see our clock cycle. Let's say our capture edge arrived a bit early. So what happens is actually we would go over here and we would say our T launch is TCQ plus T logic plus T setup plus the jitter, and the capture is again the clock period with the worst case jitter, which means it made our period shorter. The other thing is skew. So skew again is defined as positive when we're going the direction of the propagation of our signal from launch to capture. So skew, we define it as a delay in this direction. So this is going to be our delta skew. Okay. And as you see, if this is where the clock launched and then we add this delay and on the next clock cycle it's captured, what we have to do is add it to the length of the clock cycle. So the T capture becomes T plus delta skew minus T jitter. So our max constraint is that we want to make sure that the capture path is longer than the launch path. That is the race we want to solve. Okay, and that brings us to, if we kind of move around things on the sides of the equation, that our clock period has to be larger than our TCQ plus T logic plus T setup. You see that the T jitter over here is added to the T jitter over here. So we have plus 2 T jitter. So that means that this arrived later and this arrived earlier. It makes our life harder. It basically added 2 jitters of delay to the launch path, or it subtracted 2 from the capture path. And the skew, though, however, actually helped us in this case. It made our clock cycle effectively longer, so the skew comes out in a minus when we move it over to the other side of the equation. Okay, so what we understood here is that positive skew actually helps us meet our max constraint delay. So let's see that again. I just, again, moved the skew over to be in the equation as part of the capture path. So T, which is the capture path, plus delta skew, so that's this guy, has to be larger than TCQ, which is over here, TCQ, plus T logic, that's over here, plus the T setup over here, and again, jitter, in the worst case, is added twice. Okay, so that's our launch path, has to be longer, it has to be shorter than our capture path. If we look at the hold constraint, what are we going to see? So again, our launch path is TCQ plus T logic. And remember, we want that to be as big as possible because the problem with hold is that it's so fast that by the time our clock edge arrives at the capture flop, the data will already change at the input of the capture flop. If jitter makes the launch clock later, we need to subtract it from the data path delay. So now what we're saying is we're assuming a worst case. It makes our launch path shorter. So let's assume jitter made us launch early. Okay, so we have that our launch path is TCQ plus T logic minus T jitter. When we're looking at the capture path now, we want to see what skew does. So again, skew is part of the capture path. The capture path is not towards the next clock cycle. It's the same clock cycle, but still the data is arriving delta skew after the the capture clock is arriving delta skew after the launch clock arrived by definition. That's the definition of positive skew. That's how we define it. Okay, and jitter is another question. So actually, when you look at jitter is something that happens temporally between two different clock edges, and therefore, in general, it shouldn't affect hold at all because we're relating to the same clock edge. However, sometimes some of the textbooks and some of the methodologies and companies say, well, hold is such a big problem and we want to make sure that we don't fall from hold. We'll just make a worst case and we'll again add two delta jitters to the equation as well. Okay, so T capture again is 0 because that's the time difference between two phases of the same edges of the clock, plus delta skew, which is our positive skew, plus hold, and you have this plus jitter, which you removed over here and added over here, even though essentially you could get rid of jitter because we are talking about the same clock edge. So since our min constraint now is the fact that we want our launch path to be longer than our capture path, so we make sure that we capture this cycle's data and not next cycle's data, we put it all into an equation and we get TCQ plus T logic, which is basically our launch path, has to be larger than delta skew plus T hold plus 2T jitter. Again, this guy is optional. I think it's a bit of an overkill, but if you want to be extra careful, you should add it. So data has to arrive after the same clock edge has arrived at the capture register. And again, it's what we see here. We have the launch path over here, which is TCQ plus T logic. That's it, but it's going to be the shortest one under the fastest conditions. That has to take longer than T hold, which is just the constraint from the flip-flop, right? Plus delta skew, which is this guy, and we can optionally add 2T jitter just to make this case worse. What about variation? How do we deal with variation? So as previously discussed, variation in both fabrication and operating conditions occur and are taken into account through corner simulation. So as I mentioned before, when we look at global variation, and that means it's the same for all of the transistors on the chip, it's the same for all of the gates on the chip, we define three primary simulation corners. The typical corner, where our gates operate under nominal conditions of variation. Slow corner means our gates are slower, so therefore they have high VT. They're under high temperature unless there's temperature inversion, then below temperature, and low voltage. Or a fast corner, where our gates are faster, so they have a low VT. The temperature conditions are low for standard temperature or high for temperature inversion, and under high voltage. So what we want to always do is we want to assume worst case conditions, and our worst case conditions occur when in our max delay we have the slowest possible transition, and therefore we go for a slow corner, and min delay with the fastest possible transitions, which is a fast corner. However, that being said, we usually will check hold because it's so important under slow corners as well, and maybe even typical corners and with different temperatures and so forth. Sometimes you'll also check max delay under these conditions, but usually it won't be a problem, so it's not done as much. So to finish off this part of the lecture, I wanted to discuss the Computer Hall of Fame for this lecture, and I wanted to discuss the machine that made IBM the dominant computer industry to dominate the computer industry for 20 years, and that's the IBM System 360. It was announced on April 7, 1964. It was the first upgradable and fully compatible computer. Okay, so it wasn't that you just bought a computer for $1 million and then threw it away and got the next one. You could actually upgrade it. Thomas Watson, who was the CEO of IBM, bet the business on this machine. He made a $5 billion, which was really a lot of, it's still really a lot of money today, but then it was really a lot of money. He bet all of the business, basically, of IBM, of Big Blue, on this machine. He made a $5 billion investment, said it was going to cannibalize all of IBM's existing computers. So IBM had lots of different products, and he made one product to replace them all. And that wasn't a great business decision looking at it, because that's going to hurt everything else. But in the end, it was a great bet, and it won out. It was ranked as one of the all-time top 3 business accomplishments, alongside Ford Model T and the Boeing 707. So he bet the business on it, and it worked out, and it really made IBM the dominant company in the computer industry for many, many years. By the way, this machine is what pioneered the 8-bit byte. So before that, there was not this this concept of an 8-bit byte, and the peripheral components that were made by third parties. So you used to get whatever your keyboard or with your machine, and here you could make a keyboard by a third party and connect it.